Hi guys, so welcome to week 8 tutorial entitled Load Calculation Part 2. Okay, so this will be a very short tutorial video. My lecture video is quite long, so I'm sorry for that. You have to be patient and watch till the end of the pre-recorded lecture videos. Yeah? So today is the tutorial for week 9 Load Calculation Part 2. Okay, let's go to times. Hello guys, so let's go to times and straight scroll to the tutorial section and tap on week 9 tutorial. Yeah, so you have a few questions there, as you can see in the recording. 1 2 3 4, very short. Alright, so I'm going to use the answer, right, the answer there. So we have all the answer there in my PDF expert app. Okay, right, so let's go to the first question. Let me bring the highlighter there. A building has U value of 0.5 wattage per meter squared times Kelvin. So U value is the absorptivity inside the space through a window by the solar radiation. The total exposed surface area is around 384 meters squared. The building is subject to an external load only sensible about 2 kilowatt and internal load of 1.2 kilowatt sensible. Okay, so all of them are sensible. If the required internal temperature is to be 25 degrees Celsius, that means the room must be 25 degrees Celsius. State whether a cooling system is required or a heating system is required when the external temperature is 3 degrees Celsius. Okay, so technically looking at this question, we need to heat up the room because technically the outdoor air is cold, the indoor is warm. So we need to heat up the room. However, let's do this question together and see if it's true. How the results will change if the U value of the building is reduced to 0.36 watt per meter squared times Kelvin. So it changed from 0.5 to 0.36. Now let's see the answer. So this is the picture of the house and the energy balance involved in it. Right, so you have sensible heat go into the room at 2 kilowatt, and then you have heat is leaving from the house is 50.5 watt per meter squared, right? It's supposed to be, meter squared Kelvin, and the area of the house is around 384 meters squared. Right, outdoor is 33 degrees, inside is 25 degrees, and there's an internal load of 1.2 kilowatt. So technically heat is losing from this house into the outdoor space because the outdoor air is cool. Now let's see. A U value is given by 0.5 wattage watt per meter squared times Kelvin. The equation is given as such: T out balance is equals to T in minus Q solar plus Q in. Alright, so T out equal or balance equals to T in minus Q solar plus Q in the sensible divided by VA. Now, where does this equation comes from? So let me write the question here. So you will have Q M CP delta T. Okay, Q equals to MCP delta T. Erase that because I need the space. It will be Q equals to M, right? M, and CP is 1 because it doesn't given there. I've discussed this. If it doesn't give is 1 times T balance minus T in, right? Erase that. I need the space. So M, also we don't know where's our mass, so we all know that M is V times A, right? Velocity times the surface area that it moved through. This is MMA. So that is why we change the equation, becomes Q, as Q is solar plus Q int, right? So we name it as Q lah. Q, right? Or maybe a bigger Q is equals to VA and times 1, so we don't need to write that. T out, T in, right? So rearrange that, you get this answer. Okay, so indoor air is T in 25, solar is 2 kilowatt, the internal energy is 1.2, right, times 1000, right, because it's kilo, and divide by the 0.5, so that is the velocity of the heat leaving, right? So it will be U there, U value, right? Wattage times meter squared of Kelvin, 0.5. Okay, times the surface area of the house. So you get it around 8.33 degrees Celsius. So what do we see here? Since the outdoor temperature at the balance point is greater than internal temperature, T external is less than T out balance, the building require heating. Okay, so we have the T out balance 8.33. So the outdoor air is 3. So we need to heat up the room. So I know that without doing this equation, you know that we need to heat up the room, but at one point. What point? What heating load in the calculation that it needs to be. Okay, next, if we change the U value, 0.36 wattage over meter squared times Kelvin, put all that into the equation, and the final answer is 1.85. That means if the energy leaving the house is smaller, the house is nicely insulated, therefore the room is going to be hotter and hotter, right? Hotter and hotter, so the room requires cooling. Okay, so U value is important when you design a house and you want the house to be comfortable, free of hard maintenance, I mean easy to maintain, and maybe cheap, right? So which one comes first is most important. Question 2. An air-conditioned room stands on a well-ventilated basement, measuring 3 meter wide and 3 meter high and 2 meter deep, right? So that means there's a house, below the house there's a basement, right? The basement size is given as such. Okay, one of the 3 meter wall face west and contain a double glazed window size 1.5 meter by 1.5 meter. That means one of the 2 wall of 3 meters, so we have 3 meter wide, 3 meter high and 6 meter deep, right? One of the 2, so it means 2 walls of that 3 meter, because of course it has 2 walls which has 3 meter, the other one will be different a bit. It faced west and contains a double glazed glass window, so it mounted flush on the wall with no external shading. Okay, flush means you have a wall and the window is not protruding out, the window is flush into the wall. Flush, that means it's go inside. Okay, there is no heat gain through the walls other than the one facing west, because there's a glass and sun will come in during night, during close to night time, right, afternoon. Calculate sensible heat, latent heat and total heat gains of the room. Room sensibility factor following the information. What is the required cooling capacity? So this is a type where you need to do a simple calculation, but it's a long calculation. It will be given to you guys a few items there. Inside condition, outside condition, U value for wall, U value for roof, U value for floor, because each of these items has different heat transferred. Right, effective temperature different ETD of the wall, effective temperature is ETD for the roof. So each of these components have their own ETD or effective temperature difference that you must use in the calculation. not the overall temperature of the house, but the wall and the roof must have a certain effective temperature difference. You have to have U value for the glass, that means the heat can go in and out. Alright, your solar gain, that means the glass must have a solar gain because sunlight will go into the wall, and because the wall is glazed, double glazed some more, that means there's an internal shading or SC coefficient of the glass. So these are all the data given that you need to put into the equation. Last one, occupancy. Doesn't stay there, but there are 4 people there. One people will produce 90 wattage of sensible heat, 40 wattage of latent heat per person, and there's a lighting load indoors is 32.3 wattage per meter squared of the floor area. Let's go to the answer. Very simple. Oh, there's some more. Appliance load, that means all the equipment inside the house is 600 wattage sensible, 300 wattage of latent. Infiltration, that means there are leakage. We consider it as 0.5 ACH or air change per hour, and the barometric pressure is 101 kilopascal or 1 atmospheric pressure, or you can use psychometric chart that is given in the textbook, in the notes on times, and the exam. Now first we must calculate the indoor condition, 25 degrees Celsius, dry bulb at 50% RH. So from here you go to the psychometric chart. I'll get right here PC psychometric chart and find the answer, and you get your WI, inside condition. Outside, right, 43 dry bulb and 24 wet bulb. So use the PC of psychometric chart and you get your WO. Right, the density of air, we all know that it is 0.95 kilogram per meter cube. Now we will separate this calculation into external and internal. The external first, because there are a lot of things there. Heat transfer through the walls. Since only was measuring 3 meter by 3 meter with a glass window of 1.5 meter by 1.5 meter exposed, heat transfer through that wall, through that window, is given as such. So let me draw. This is the wall, right? 3. However, there's a door there. 1.5, 1.5. So this is a window, and this is a wall. Okay. Q wall is equals to U times A times EPD. So this is a Q without using any MCP delta T or enthalpy, but the effectiveness temperature of that component. Right, U wall is given as 1.78. If it's not given, a table will be given to you and you can choose these numbers from that table. Okay, A is 9 minus 2.25. That means 3 times 3 is 9. 1.5, 1.5. 1.5 times 1.5 is equals to 2.25. Okay, times 25. Right, times 5, you get 300.38 wattage sensible heat. Okay, so why it's 25 there? Because this is the ETD for wall. So for heat transfer to the roof, the same equation, you get 710.6 sensible wattage. Through floor, right, since the room is stand on a well ventilated basement, that means the room has a basement and the basement has some windows. We can assume that the condition of the basement to be the same as outside. Now this is very important. If there's a well ventilation of that space, the condition will be the same as outside. This must be incorporated in your mind when you do this sort of question. Alright, so it will give you the condition of the outdoor as well. Since the floor is not exposed to solar radiation, the driving temperature difference is between the outdoor and indoor. There's only one method heat can escape or go into, which is just the indoor and outdoor wall or roof. Okay, so through the floor is U floor A, and ETD is 1.2 times 18 times 18 for ETD, and you get 388.8 sensible heat. Next is heat transfer through the glass pula. They consist of radiation as well as conductive components. No information is available in the value of CLF. Right, let's find what DCLF in the note. It is taken to 1. If there is nothing given, CLS or coefficient of the glass transfer, that will be 1. Hence the total transfer heat rate to the window is given by Q glass A, U glass T outdoor and T indoor plus SGHF max plus C. So 2.25 is the glass area. U glass is 3.12. If it's not given, then table will be given times 18 plus SHGF and also SC, and the answer is 706.9 wattage, and this is still sensible heat. Now infiltration reaches 0.5 air change per hour. Converting this into mass flow rate, infiltration is in kilogram per second. That means you need to divide by 300,600 seconds. Yeah, so you see density of air is 1.095. ACH and the volume of the room is 0.5 to 3.3 times 6 divided by 3,600. That is to change hour to second. And the answer is M infiltration 8.2125 times 10 to the power of negative 3 kilogram per second. Okay, now sensible heat, because this infiltration is connected to outdoor, there should be humidity coming from outdoor as well. So you need to separate into two parts somehow. One is sensible heat, one is latent heat. So QS for sensible infiltration equals to M infiltration times CPM times T delta T outdoor and indoor. So MF is 8.2125 times 10 to the power of negative 3, which we have calculated just now, right? And then times the CPM, which is given, and the difference of the temperature, and you get 151 wattage plus sensible, right? And this one is Q latent infiltration, M into HFG, and then delta omega. So this one is for latent, so this is wrong, latent. So put all the answer, you get 16.4 wattage. Now we have covered all the external, we go for the internal. Load due to occupant, sensible and latent heat, so it's given already, times how many people, 360 watts and 160 watt respectively. Due to lighting, Q is 33 times floor area, we get 594 wattage, sensible as well, because there's no heat water coming from devices. Load due to appliances is, you need to calculate, it's given already. Alright, so total sensible loads are obtained by summing all sensible electric components, right? So you have QS total is that, QL total is that, right? 3,811.68 wattage and 474 respectively. So you plus them all together is around 4,288.08 wattage. Room sensible factor is given by, so it's given by this. So from there you find your QS, right, which is this, and Q total is this, and you get your RSHF 0.889, which you can use on the psychometric chart to continue to do many other calculations as well. To calculate the required cooling load capacity, one has to know the losses in return air duct. Ventilation may be neglected as infiltration and can take care of small ventilation requirement. Using safety factor to 1.25, the required cooling capacity is, right, 5360.1 wattage or 1.5 TR. Okay, 1.25 safety factor is used by the industry to study the safety factor without overloading the calculation. Okay, question 3. A large air-conditioned building with a total internal volume of 100,000 meters cubed is maintained at 25 degrees C, this is dry bulb temperature, and 50% RH. The outdoor condition is 35 degrees Celsius and 45% RH. If the design occupancy is for 10,000 people and it must be non-smoking, the infiltration through the building is equal to 1 air change per hour. Estimate the heat transfer rate due to ventilation, infiltration, and assume the barometric pressure to be 1 atmosphere. That means you can use the psychrometric chart. Okie dokie. So this is our condition there. As you can see, use your psychrometric chart to get all this data. Alright, so ventilation, as a table should be given to you, is 3.5 liter per second per person, right, equals to V naught. So 3.5 times 10,000, because there's 10,000 people going to be there, is around 35,000 liter, right, per second. Change to meter per second, divide by 1,000, you got 35, right? And from there you get your MAV, which is 35 divided by 0.859. So you can get this from here. Okay, so what does it mean? It means your M is equals to velocity divided by specific volume, right, which is available on psychrometric chart. Sensible heat factor is QS mCp delta T. Okay, so here is V for vapor. Putting all the answer, you get 399.5 kilowatt. But latent heat factor is different. QLV is times MV, and HFG times the difference in omega. And you get the answer to be 649.3 kilowatt. Okay, so then you combine together, the answer is 104.8 kilowatt. So the filtration is V infiltration equals to 1 SH 100,000 meter cube divided by second, because we want to change from hour to second. So you get 27.78 meter cube per second. And from there you can calculate your MF to be 31 kilogram per second, and you get all your answers as such. Okay, it's very easy. The last one, calculate the maximum heat transfer rate through a 1.5 meter square area, unshaded, regular double glass facing south during the month of June and December, without internal shading, and with internal shading consists of light Venetian blind. Location is 32. Okay, so 32 means you can use location given in a table, right? So what table? If you go to your notes, right, open your notes again, on the appendix there is a shading coefficient there. So this table is used, and you can also use some of the table there. For example, this is solar time. What else? I think we can go up, and here is the orientation of a surface facing whatever direction at 32 degrees north, right? There is there. And also Venetian blind. So this is the Venetian blind, right? You can see there, the one that you have in campus as well is called Venetian. That means you can open and shut within a. Okay, so in the month of June, SSGF max from table 2 solar radiation is 190 wattage per meter squared. So let's go back to our notes. In June, right, and it's facing south, and it is 190, as you can see there, right, 190. Okay, which is that one. All right, without internal shading, the SC is 0.9. So QSG solar gain is A times SHGF max times SC is 1.5 times 190 times 0.9 is around 256 wattage. Alright, so if you have internal shading, there's the Venetian blind. You can go back to that notes. Venetian blind, let me see, Venetian blind. Okay, the Venetian blind and minimum for single glass or double glass is 0.57 medium. Okay, so you put it there, 0.51, and you get QSG solar gain with internal shading is lower, lower 145.35. So in the month of December, use the December, and you get without internal shading 73.25, with internal shading 608.17. Alright, questions 5. Okay, The last question. Calculate energy transmitted to a building at 3 p.m. on July 21st due to solar radiation through a south-facing window made of regular single glass. The dimension of the windows is 2 meter, width 1.5 at the depth of 0.3. Find the energy transmitted when there is no overhang. Overhang is like awning, right? Awning outside the window. Here it says 32 degrees north. We can use the equation. So the altitude angle is given by this equation, or I can just straight ahead give to you what is B and alpha, beta and alpha, right? So wall solar azimuth angle H, L and D is given, and you get all these results. So you need to see the area unshaded, X, X, Y. So X is W minus D, D is depth, and Y is height minus depth. And you have your equation there, alpha and beta. You put all them, you get X is 1.249 and Y is 1.562. So heat transition rate QUS XY times SSGF max from the table times the shading coefficient, you get 448.7. If it's shaded, you get the answer is 125.9 voltage, and the total is US plus HH. SS is 574.6. So if you have a without overhang, QSG only is W times H. SSGF equals to 690 watts of savings, right? The energy transmitted without overhang. Okay, so that concludes our questions 1 to 5. It's very simple. You can contact me if you need any help. Thank you for your time for week 9. It's very easy, but a lot of calculation. So I would say the supplementary chart has a lot of calculation. The solar radiation has a lot of calculation, and most of them are memorizing or applying your knowledge in the evaluation section. Alright. Okay, so that's all for week 9 tutorial, load calculation part 2. I'll see you on our final lecture and tutorial week 10. Right, see you around. Don't forget to see me in the meeting, yeah? Bye.